In this video, we're going to look at limits at infinity looking at rational functions. I've just written rationals, but rational functions. Okay, so let's say, for example, we were asked to find the limit as x goes to infinity of x minus 1 over x plus 5. All right, and then let's say, actually, let's make it a little bit more exciting. Let's write a 2 in there. Okay. And then let's say I was asked a different problem, and this one looks like that. Okay. And let's go ahead and write one more. Let's write a minus, because sometimes students go, does it matter if it's plus or minus down there? No, it doesn't. It doesn't matter at all. Okay, excellent. So here we go. So I have 3 different limits. And as you can see, I very rapidly made some up. But what you want to do when you're given rational functions with limits going to infinity is that I want to look at the degrees of the top and the bottom as they relate to each other. Okay, so remember, degree means biggest exponent. So here, the biggest exponent is x to the first. So this would be comparing the degrees of the first rational function. This one is x squared over x. And this one is x over x cubed. Okay. As you can see, I have 3 very different examples. All right. Here are the rules. First off, what's going on here is we want to know, is the one side, either the top or the bottom, dominating the other, or are they kind of keeping pace with each other? Okay. So let me first talk about dominating one over the other. So, for example, in this bottom example here, x cubed, right? X cubed is going to grow way faster than x. So if I were to plug in a number like 10, the top is a 10, or the bottom is 10 cubed, which is 1,000. So this is 10 over 1,000 minus 2, so it's going to be a small decimal. Okay, so what happens here is when the degree is bigger on the bottom's going to grow huge. So you'll even see sometimes in my notes, all right, huge, okay? So it's going to grow huge, so it's going to slam the whole thing to 0. Okay, so quite honestly, if in your homework, what you could do is you can just circle that and write 0. I know what you're doing. I know you're saying that the bottom is growing faster than the top, so it's going to be a huge number. When I divide that, actually, it's going to make an overall small number, so it's going to 0. On the flip side, when the top is dominating. So here, if I were to plug in a number like 100, this would be 100 squared divided by 100 plus 4. The top is growing way faster. Even though this is going to take a chunk out of it, this is still going to grow a lot faster. So when the top grows faster, it's dominating. So what's happening here is, and this is another thing you'll see in my notes, you'll see that I'll write that this is going to act similarly to x squared over x. Okay, and x squared over x is x. So what happens when I plug in x goes to infinity if I just have x? I just get infinity, right? So what's happening here is when the degree is bigger on top, it makes the whole thing overall blow up to be infinity. Now, it does matter whether it's positive infinity or negative infinity. So in the next video, you'll see another example of how that could affect our answer. But in general, yes, it's going to become huge. All right, let's go to the very top one. As you can see in the top, the degrees of the top and the bottom are the same. What's happening here is that they are keeping pace with each other. So this is going to act like x over 2x. Okay, and as you can see, what happens when I have x over 2x? How can I reduce that? Yep, I can reduce that to 1/2. So what's happening is that this is going to 1/2, which also happens to be the horizontal asymptote. So when you have a rational function where the degrees are the same, top and bottom, you can always do this, and that is telling you where the horizontal asymptote is living. Okay. Now, since we're talking about horizontal asymptotes for a second, let's talk about this guy. If I'm going off to infinity, there's no horizontal asymptote. There's nothing that's keeping me flat or attracting me to it. This one, this number of 0, this is also a horizontal asymptote for this function. Okay, horizontal asymptotes are basically a line, and that line, like for example, this guy's, that line's at 1/2, and it acts like an attractor to the function. So that I can't just shoot off, it's going to attract to it. So it'll attract the sides down to it and attract the sides down to it, so that way it's not shooting off to positive infinity or negative infinity. So when I say shooting off, I mean shooting up and out. That wouldn't be possible with a graph like this, because that asymptote's acting like an attractor, kind of like a magnet, saying, no, chill right with me. Okay. We're going to have more examples of this in the Zoom lecture and in my notes, and then we'll have another couple videos, okay? So hang in there. This stuff gets a little bit tricky, but if you persist, you can do it.